Okay, so let's start. So today's lecture is going to be on processor scheduling. This is a little bit out of order because normally we would cover process management first. What's a process? How does the OS create processes and so on. Then we talk about how to schedule them. But I wanted to do it a bit out of order because I think the next lab might require you to do something with CPU scheduling. So I wanted to get that material out first, and then we can go into the details of process management in MINIX and things of that. Okay. So today's class, there are three things I'll talk about. First is what is processor scheduling, what are the goals of scheduling processes. Okay. The second one is going to be a refresher on CPU scheduling. This is actually that second point is a material from an undergrad OS class. Okay. So depending on how much you remember or how little you remember, we can speed it up or slow it down. It's entirely going to be based on what I'm going to ask you some questions, and depending on how much I see all of you knowing the material, we can decide how much time to spend on it. Okay. And the third part is, of course, how does MINIX do it, right? What does CPU scheduling in MINIX look like? And we'll see the concepts actually directly translate to a nice implementation in MINIX. Okay, so it's no surprises there. Most OSs will do their own thing. This one does more of a textbook style model of scheduling, as we will see. Right. So let's start with the first point, which is goals for processor scheduling. So this picture essentially shows us the process state transition diagram, which we haven't encountered yet. We'll get back to this when we talk about process management, but by and large that figure says when processes start, they are in a new state, and then through their execution cycle, they cycle through essentially ready, running and wait. In a ready state, a process is actually ready to execute on the CPU, it's just waiting for its turn to run on the CPU. The run state is actually executing. If it does any I/O, it sits in a wait state, waiting for that I/O to complete. Okay. So you cycle through these states, and eventually you are done executing, you go to terminate. Okay. So that's the thing you want to keep in mind. The goal of the CPU scheduler is essentially to decide of all the processes that are in that ready state, which one is actually going to execute next. And you'll see that there's one process, if you look carefully at the right above the running state, there's one process. In a single processor machine, there can be only one process executing at any given time. Right. Of course, in a multi-processor system, multi-core system, there will be as many executing processes as the number of cores. Okay. That's the limit on the number of processes executing. Okay. So our goal is to design in a multi-programmed system a CPU scheduler. And multi-programming again only means the ability to run multiple processes concurrently on your system. Uniprogram system says you can only run one application at a time in addition to the OS. Multi-program one says you can run multiple. Okay. So that's the definition of multi-programming. So now let's talk a little bit about how scheduling works more broadly, and then we'll talk about specifically processor scheduling. So in any OS, and it depends on the flavor of the OS, there are two kinds of decision being made. One is called long term scheduling and the other is called short term scheduling. Okay. Long term scheduling is looking at how many processes can that system accommodate at any time for concurrent execution. Okay. And the answer to that is going to depend on things like how much RAM do you have. Okay. You cannot create unlimited number of processes and expect them to run. Eventually, your system will run out of resources. Okay. So the goal of the long term scheduler is to police the entry of processes into the system. So you will see here that there is essentially a queue. So newly arriving jobs enter that queue. The long terms in this, the one part of the long term scheduler here, which is called the admission scheduler, is checking. Okay, have we run out of resources to admit yet another process in the system? If so, you are not going to let that process run. Okay, if not, you will basically let it actually become a real process and start executing. Okay. And there is another part of a long term scheduler which you do not see often, but it is called the memory scheduler, and its goal is maybe there you have maxed out your system resources, you want to let another process in. The only way you are going to do that is to take an existing process that is executing, temporarily swap it out to disk. Okay. That is what that memory scheduler is doing. It is swapping entire processes in and out of memory just when you run out of resources. Okay, so the two collectively do long term scheduling decisions, which basically decide how many processes are actually in executing actively, not necessarily in memory, because you could be using virtual memory, but how many are active processes in the system. Okay. And then the short term scheduler is the one that you see at the top, that is called the CPU scheduler. Of all the processes that are currently active and ready to run, which one gets to execute next. Okay. So, that is the goal of this and that is what we will call a CPU scheduler. We will not actually use the term short term scheduling, but we will use the term CPU scheduling. Okay. So, what I just said on the previous slide is just summarized here. So, I am going to just skip this slide. Okay. So, now when does the short term scheduler run? Okay. So, the short term scheduler or the CPU scheduler is essentially a core function of the OS kernel. Okay. So, it is going to get invoked when one of a few different events actually occur. Okay. Those are listed there, saying if a process is if a process is switching from running to waiting, if a process that is executing blocks, okay, the CPU becomes idle. Okay, because the currently executing process is blocked. So, then you run the CPU scheduler saying what next. Okay. Then if there is an interrupt, same thing happens, okay, because the interrupt handler is going to run, and then once the interrupt handler is done, you have to say what should I run next. Should I resume the process that was running, should I run another process, all of that is going to be decided by the CPU scheduler. Okay. Of course, if a process is created or terminated, you also have to run the CPU scheduler. Okay. So, the CPU scheduler is going to run when all of those things happen, okay, and we will see that there is one more event that can occur that triggers the CPU scheduler, but for that we need to define two terms, non-preemptive and preemptive scheduling. Okay. Non-preemptive scheduling says once a process starts executing on the CPU, you cannot actually preempt it, okay, which means that the scheduler cannot say that something else has to run. It can run for as long as it wants, okay, until it blocks or terminates. Okay. That is a non-preemptive scheduler. Okay. Most schedulers you see are not non-preemptive, they actually fall in the preemptive category, and as the name suggests, a preemptive system is one where the CPU scheduler can interrupt that process, or the OS can interrupt that process. Okay. And so, this is used in the context of what is called quantum based scheduling. Okay. Whenever a process runs, it is given a fixed time quanta, okay, and say that is the amount of time slice you have. It can use its entire time slice, at that point it is preempted and something else gets to run. Okay. So, in preemptive scheduling, in addition to those three things that cause the CPU scheduler to run, there is a fourth event which is quantum expired. Okay. When the quantum expires, the scheduler will also run and say what gets to run next. Okay. Is this clear? Okay. So, now let us talk a little bit about some of these policies. So, before we do that, it is good to understand what process behavior looks like, so we can design policies that are designed for various kinds of process behaviors. By and large, when you run a process on your machine, it will fall into one of two categories. It will either be CPU intensive or IO intensive, okay, at any given instant. Over the lifetime of that process, it can switch from being CPU intensive at any point to IO intensive and back to CPU. But at any given instant, you can classify a process as either being CPU bound or IO bound, and as the name suggests, CPU bound processes are ones that need a lot of computation cycles to execute. IO bound processes spend most of their time doing IO. Okay, those are the two things that are shown in the picture. Okay, the x axis is time. Okay, whenever you see a gray bar, that means the process is actually executing, and then anything in between, that means it is not executing, it is blocked. Okay. And you will see that for IO bound processes, there are short bursts of computation and then long periods of IO. Okay. And for CPU bound processes, it is the opposite. There are long bursts of computation and maybe short bursts of IO. Okay. And we will come back to this when we think about what scheduling policies make sense for scheduling processes that exhibit one or the other behavior. Okay. Any questions on this? All right. So, now let us talk a little bit about goals for scheduling. Okay. So, what are we trying to achieve by scheduling processes? Okay. You can define various metrics and say the goal of the CPU scheduler is to optimize which could be mean, maximize or minimize depending on the metric, one or more of those metrics. Okay, and then there are several listed here. CPU utilization says the percentage of the time CPU is busy. Okay, throughput says the number of processes that finish per unit time. Turnaround time says the time from start to the end of a process. Waiting time says how much time is it waiting in the run queue, waiting for a ready queue, waiting for a turn to execute. Response time says how responsive is it to I/O and so on. Okay. These are different metrics that you will see in a system. Okay. Now, you might think these are all good metrics to optimize. Okay, why not try to optimize all of them? As it turns out, any scheduling policy can optimize some of them at the expense of others. There is no policy that can actually optimize all of them together. So, you have to pick what makes sense. Okay. If your machine is going to run lot of interactive jobs, if the user sitting and interacting with a graphical user interface, you want to minimize response time. So, the system appears to be responsive. Okay. If your machine is going to run a lot of batch jobs, maybe you are doing batch processing, you are running machine learning computation, whatever it is, you want to maximize throughput, you want to maximize the number of jobs that are finishing per unit time. Okay. So, different metrics will require you to use different CPU scheduling policies, as we will see. Okay. Now, what I just said is actually summarized again here, which essentially makes that same point I said, saying if you are a batch system, you want to essentially optimize these metrics: throughput, turnaround time, CPU utilization. If you are an interactive system, you want to optimize response time, proportionality, which is, I didn't define it, but it says meeting user expectations. You could have other kinds of system like real time system. Okay. So, these systems are maybe systems that are in your car or that are in an airplane, that are controlling mission critical systems. In those systems, you have completely different class of schedulers that try to meet deadlines, that give predictable guarantees, that can guarantee that such the task can finish in a certain amount of time and things of that sort. Okay. We are not going to look at real time system scheduling. There is an entire class of scheduling algorithms and policies that are designed solely for that class of system, but we will not look at that. We are going to focus more on general purpose systems which fall into the batch and the interactive category. Okay. Yes, question. Okay. Question is, in the scheduling policy where your long term and short term scheduling, is there any priorities and things of that sort? So, there are no priorities because they run and operate at different levels. The long term scheduler is only looking at new processes that are starting. Okay, typically, well, at least the admission scheduler, not the memory scheduler, and the CPU scheduler is only looking at processes that are active. It does not actually look at processes that start. So, they are actually invoked at different points in time. Okay, so, there is no priority per se. They are just doing two different things in the system.
But they need to be sort of synchronized together so that the CPU scheduler doesn't try to run an instruction of a process which already got swapped out or something like that.
Okay. So, now the question is, they need to be coordinated, so you cannot run a process that has been swapped out. Okay. So, you will actually have data structures in the kernel, which is called the process table, that will tell you the state of each process. So, if you swapped out a process, it should not be on your run queue, it should be in the wait queue, right, because it is waiting to be swapped back in. Right. So, there are things you will do to make sure the cases that you are mentioning do not happen. Other question. Okay. So, let us go through policies that CPU schedulers use, and as I said, that part is really a refresher. So, I am going to present them and maybe see how well you remember them or not, and then we will decide how much time to spend on each. Okay. So, this I already mentioned, which essentially says a scheduler cannot optimize all the criteria together. So, you got to pick depending on what system you have. Okay. So, now as far as the scheduling policies I am going to present are concerned, we will start simple. Okay, because it is easier to understand. We will assume that each user has only one process, not true in practice obviously, users can start as many processes as they want. We will also assume that processes are sequential, they have no threads, okay, one thread which is a sequential process. Again, not true in practice because you cannot threaded processes. Let's assume processes are independent, which means they don't interact with one another. That's also not true because processes can communicate and then they are not independent. Okay, and then we'll say single processor, single core, which most systems today are not. Okay, but this is a set of simplifying assumptions for us just to understand how the policies work. But in reality, none of those assumptions may be true. The policies have to deal with all of those issues. Okay. So, let us start very simple with first one, which I think does not really need a lot of explanation. We will do first come first serve, okay, which is FIFO. Okay, that is a very simple policy. Okay, you basically schedule processes in the order in which they have arrived. Okay. Let us think about this and say, is this a preemptive or a non-preemptive scheduler? It is a non-preemptive scheduler, okay, because essentially, as the name suggests, you essentially once you schedule that process or for execution, it is going to run for as long as it wants, because that is the concept of first come first serve. Okay. Now, there are two variants of FCFS. One, which is an early one, says the job does not give up the CPU even if it is doing I/O. Okay. So, that means actually going to run all the way to completion, and even it may have long bursts of I/O which will idle the CPU, but you are not going to schedule anything else in that period. Okay. More modern variants do not do that. Okay. They are not going to preempt the process, but if the process relinquishes the CPU because it wants to do I/O, it is blocked on a lock or something like that, then something else gets to run. Okay. That maximizes CPU utilization, it does not idle the CPU needlessly. Okay. So, that is FCFS. Yeah, there are some advantages which is very simple. Disadvantage is that the waiting times are highly variable in FCFS. Okay. A waiting time essentially says how long are you waiting in the run queue to get a turn to execute on the CPU. Okay. Is it clear why there is more variance in waiting times? Yes. So, tell me why. Okay. Process lengths are different. Okay. It is like you are driving on the highway and you are stuck behind a truck, right. So, there is a long vehicle that is slowing everything down. The same thing is true here. If a long job runs before a short job, okay, that job is going to make the short job wait for a long period, because FCFS says you cannot run the short job until the long one is done. Okay. So, depending on the arrival order, you might have high variance in running. If the short job had come just before the long job, everything would be reversed. Okay. The waiting time for that arrival sequence would be much lower. Okay. So, it depends on the arrival order and it can be highly variable. Okay. So, here is a simple example which I am not going to go into too much detail, just shows you how FCFS works and it kind of makes the point I said. So, first one is BCA are the three processes that arrive, they execute in arrival order. Okay. And the second one A, B, C arrive, okay, and A is longer than B and C, as you will see. So, in some sense B and C have to wait longer than in the previous sequence, because they essentially their B and C are shorter jobs. Okay. So, the third example is just showing you what happens when you do I/O, okay, which basically says if A makes any blocking calls, once it arrives, then it has to relinquish the CPU, B gets to run, and then if its I/O is done, when B completes, it can resume execution. Okay, yes, question.
So A basically just jumps to the back to the front of the it jumps to the front of the queue.
Right. The question, yes, that is a good question. The question is, if A has relinquished the CPU, B runs, then and A is again done with its I/O, does A gets to run again? Is it at the front of the queue or the back? In FCFS, since you are scheduling in arrival order, what you do is you look at all the jobs that are ready to run, you simply sort them in arrival order. So, A has arrived first in the system. The fact that it went off to do I/O did not change that, it was still arrived before C. So, it still gets to run in this case. Okay.
My one other question is, let's say, so if A's I/O takes like 1 second, but B's runtime is 5 seconds, is the CPU going to work on B for the entirety of the 5 seconds until A?
Right.
And then only afterwards does it finish up A?
Right. The question is, if A does a short I/O and B is longer process and is executing, does A have to wait? Remember, this is a non-preemptive scheduler, right. So, once something runs, you do not interrupt it. So, B's I/O is done, B arrived first, but A's I/O is done, A arrived first, but B is executing, can't preempt it until it finishes. So, it will actually have to wait. So, you will still see that order there. Okay. That is true of any non-preemptive scheduler. Any other questions? Okay. Let us move on. So, the next one is also very straightforward. This is called round robin scheduling. Okay, as the name suggests, in this case you are executing jobs in some round robin order. All right. So, you are basically going to have a queue of jobs, you execute one, goes back to the end of the queue. Once its time slice expires, then you run the next one, and so on and so forth. Okay. So, is this preemptive or non-preemptive? Okay, it has to be preemptive, because if round robin is made non-preemptive, it degenerates to FCFS. Okay, FCFS is essentially round robin in a non-preemptive fashion. So, here every job is going to be given a time slice, also called quantum. Okay, that is the duration for which, when it is scheduled for execution, it gets to run. Okay, if it uses its entire time slice, it has to go back to the end of the queue. If it blocks in the middle of its time slice, okay, it is going to go to the wait queue. Okay, and when it is done with this I/O, then it comes back and joins the end of the queue. Okay, so, that is basically what is going to happen in this case. So, that is simple round robin scheduling. Okay. Now, one issue with the round robin schedulers is how large a time slice to pick. Okay. That is the only parameter really that you have in round robin scheduling that you can play with. Okay. And depending on the time slice that you pick, you will get different properties. Okay. Let us say you pick a small time slice. Okay. Now, you are rapidly cycling between processes, because each of them gets to run for a short period of time, you switch to the next one and next one. So, every process gets to make some progress for a little bit of time, and then they give up the CPU. Okay. So, that is good, because it allows every process to make some progress, but in this case there are a lot of context switches. You are switching between processes. Okay. The thing that you have to remember is, when you switch from one process to another, there is some bookkeeping that the OS has to do. It has to save the state of that process and load the state of the next process. That means essentially all the registers have to be saved, the stack pointer, frame pointer, all those have to be saved somewhere. You have to load the next process's registers and so on. All of that incurs some overhead. Okay. It may be small, but it is not zero. Okay. So, the more context switches you have in your system, the higher that bookkeeping tax you are paying in that system. Okay. So, more responsive, but higher overheads. Okay. Now, on the other hand, if you pick a long time slice, everything is inverted. Okay. So, now essentially have fewer context switches, okay, by definition, because you have longer time slices. Okay. But and each process gets to run for longer periods of time, but each process also has to wait for longer to get a turn on the CPU. Okay, so, you are going to have this overhead. So, then the question is, what is the right balance between responsiveness to jobs and the amount of overhead you pay. So, typically those factors are going to determine what time slice you are going to pick for a certain system. Okay. It is good to keep the overhead small. So, typically you do not want the overhead to be too high. So, the quantum size is chosen so that the overhead is less than 1%. That is a rule of thumb, that is not a requirement, of course. Okay. So, many systems will have 10 to 100 millisecond quantum slices. Okay. Some might have shorter, some might have a bit longer, but that is still by and large what many systems are going to do. Okay. All right. Any questions on this? Okay. So, there is an example here which I am actually going to skip, because that is undergrad exercise, which you can go back and look as a homework later on. Okay, that just shows how the two work and then what waiting times you see. The only thing I want to point out is, if you take the same jobs and you schedule them using FCFS and using round robin, and you calculate the wait times, you will see that the wait times are actually going to be different. In this case, actually the round robin has higher wait times for this arrival pattern, because remember, FCFS can be highly variable in terms of its wait time. Does not mean that FCFS is better, just says that all of the jobs finish more or less at the same time. The wait times end up being higher for round robin. Okay. So, that is something you want to keep in mind. Okay. It is more fair, but then in some cases the wait time goes up. Okay. So, we will come to the next one, which is shortest job first. Okay. Does anyone remember what this is? SJF. Yes.
It just orders the list of jobs starting with the shortest versus the longest.
Okay. So, you order jobs by their lengths, and as the name suggests, you pick the shortest one for execution next. Okay. Preemptive or non-preemptive? Okay. It can be either actually. So, the non-preemptive version is called SJF. The preemptive version is called shortest remaining time first. Okay. So, you can essentially time slice, and at the end of the time slice, you can again pick the shortest job, and the one that you are executing has just become a little shorter because it executed for one time slice. But if a new job has arrived in that period, that's even shorter, it will get to run. Okay. So, SJF by definition is not preemptive, but SRTF, which is its preemptive variant, can actually use time slicing. Okay. So, you can have either one. All right. What is good about SJF and what is bad about it? Yes.
The bad thing is you can't know how long a process is going to run for in advance.
Okay. So, one downside of shortest job first is that it requires knowledge of the job length. Okay, where is that coming from? Yes. Okay, you can only estimate it. At no point when you ever started a process or a browser did the OS says how long are you going to run it, right? Users don't know anything about job length. OS doesn't know anything about job length. So, you can't really know what job lengths are. Only thing you can do, as was pointed out, is estimate. You can use past history saying when this job ran previously, it ran for this long. So, I estimate that it might run this long, but that's an estimate, that's not a guarantee. Okay? So, it is by definition, since job lengths are unknown, you cannot actually implement this in practice unless you have a way to estimate that length in some accurate fashion. Okay? Otherwise, it's not practical to implement. Okay? So, that's the downside. What's an upside of this policy? Yes.
Shorter jobs can be done quickly.
Okay. Shortest jobs can be done faster. Okay. You had something.
Low turnaround, right? High
Okay.
turnaround.
Okay. Turn around.
Max.
Okay. So, your more short jobs finish, but what does that do to the system? Okay, it's the only policy, if you actually read it's all said there. The first advantage is provably optimal waiting time. It's the only policy that actually minimizes waiting time across all processes. There's no policy that can actually do any better. Okay, it's optimal in terms of wait times. Okay, because it's actually preferring short jobs and getting them out of the system as quickly as possible. The wait times that jobs see are going to be as small as you can make them. Okay. So, that's actually the only reason we even study this policy in operating system textbooks is it has that property which you want in a practical implementation. You cannot implement SJF, but any scheduler that you want to implement, we would like to have that policy because good low wait times is a good thing. Okay, yes.
But if in case of SRTF, if the time quantum is smaller than the smallest job, then it won't finish right before that, it will go back.
Yeah. So, what happens in SRTF if the time quantum is smaller than the length of the job, right? So, let's take an example. Let's assume time quantum 1 millisecond, length of the job 5 millisecond. Okay. Another job comes as 10 milliseconds, two jobs, 5 millisecond job, 10 millisecond job. Okay. You are going to pick the shorter job first. Okay. We will pick the first one. You will run it for a millisecond. Okay. Now, what happens? So, after the job finishes, yes. Right. So, in SRTF, if there are no new arrivals, it basically turns into SJF because the shorter job keep getting even shorter because it's executed for some time, it will run again. Okay, this is not doing round robin. It's not going to the end of the queue. It's just looking at all jobs and saying what is the shortest job or shortest remaining time, which is what is the job the time left on this job. That's what it's checking. So it won't vary from SJF. Yes. Is there a time quantum in SJF? SJF is not preemptive, so it does not have the notion of time quantum, but SRTF is a preemptive version of SJF which actually has time quantum. Okay, so there are two variants. Any other things here? Okay, last thing that is bad about SJF is it can lead to starvation of long jobs. Okay, so it has low wait times because it's preferring short jobs, but if there's a steady stream of short jobs arriving and there's a long job that arrived some time ago, it will never get to run because short jobs are always preferred, and that's something you don't want in a practical policy. Okay, so you want to do two things. You want to get the low optimal wait times or approximate it in a practical policy, but at the same time you don't want any starvation either. Okay, so those are the true properties we will try to actually extract from SJF and see how to get it in a different policy. Okay, all right. So we'll skip the example, but you will see that the wait times are the lowest for SJF if you actually work through that example. So what we'll now do is start looking at what actually most OSs do. We'll start with priority scheduling and then we'll make that a little more complicated variant of priority scheduling. So let's start with what is priority scheduling. That picture is actually a good one to keep in mind. Okay, in a priority scheduler, you essentially do round robin scheduling, but you have multiple priority levels or multiple queues. Okay, you do round robin in each queue. Okay, but you start always with the highest priority. You do round robin in that queue. When that queue becomes empty, you go to the next highest priority queue that's not empty. You have to keep doing round robin and so on and so forth. Okay, so if these were the only jobs in the system, no new jobs arrive, you will essentially, and I'm assuming in this case 4 is the highest priority, so you will do round robin at priority 4. Eventually those jobs will finish. Okay, then that queue is empty. Then you will do round robin at priority 3. Eventually those jobs will finish, and then 1 and so on. Okay, of course there will be in a real system arrivals in the system that will change that behavior, but that's what you should expect. Okay, so it's called priority scheduling. Keep in mind that in a priority scheduling there are a few things to keep in mind. It can have starvation problems. Okay, if you are a low priority job and there's always a high priority queue that is non-empty, that low priority job will not run. Just as in SJF, the longer job didn't run. So it can face starvation. Okay, that's something you want to keep in mind. The second thing you want to ask is, who is going to decide the priority level of jobs? Where is that going to come from? Any thoughts on that? Who's giving priorities to jobs? Process manager. Right? Process manager could assign priorities. Okay, there are only two entities that can give priorities, user or the OS. Process doesn't decide its own priority, process just runs. Okay, it turns out that you can actually have both of these. Users can assign priorities to jobs, OS definitely assigns priorities to jobs. Okay, whenever you start a process, it will have a default priority. Okay, you can actually use some commands to assign priorities to your own jobs. Okay, anyone know what that is in Unix? Okay, nice. So nice is a command that allows you to change the priority. So if you say nice process ID and give an integer that's a priority level, the OS will actually choose that to be the priority. Okay, typically, as the command nice suggests, it was put in place so that you can lower the priority of your job to be nice to another user. Okay, but of course you can increase the priority of your job as well. All right, so users can change priorities of jobs. The OS by default gives priorities, and you'll see in some schedulers they can change the priority dynamically. Okay, and then of course there will be more important things in the system that you want to run at high priority. Okay, that includes the kernel itself, system processes and so on, device drivers. So you run all of those at high priorities, maybe user processes run at slightly lower priorities. Okay, so that's how you're going to assign priorities to jobs. But keep in mind you will still have starvation if you don't do this carefully. Questions on this? Okay, so now let's go to what is a variant of a priority scheduler that incorporates some of the features of multiple scheduling policies we have talked about. Okay, The name of this policy is multi-level feedback queue or MLFQ. You might remember some details from our undergrad course, but let me go into that again because this is also the policy that MINIX is going to use. Okay. First and foremost, MLFQ is a priority scheduler. Okay. Simple priority scheduler. It has multiple priority levels. Okay. Within each level, you are going to do round robin scheduling. First property of MLFQ. Anyone remember anything else about MLFQ? Yes.
Everything gets reset.
Everything gets reset. Can you explain what that means?
So after a while, a certain time quantum, all the processes that are, or all the processes get bumped back up to the top, so that they don't get stuck behind, so that the slow moving process doesn't get stuck and never completes.
Okay. So you are talking about a property that essentially allows you to avoid starvation, right? So what MLFQ does is, if a process is stuck in a low priority queue for a long time and hasn't gotten to execute, it's going to bump it up one priority level, saying maybe this job is starving, let's just increase it up priority a little bit so that it might get a shot at the CPU. Okay? But we'll come back to the starvation problem at the end. That's just put in place to avoid starvation. Let's talk about what is there in the policy that is interesting. Anyone remember any more details? Yes.
I think it prioritizes IO bound processes.
Okay. So MLFQ prioritizes IO bound processes. That's true. How does it do it and why does it do it? Yes.
If a process stops using the CPU for some reason, or presumably to do I/O, it keeps it at its current level because it assumes that it's going to keep not using its full time quantum.
Right.
But if a process uses its full allotted time, it bumps it down because it assumes it's a slower moving process that isn't going to be performing much I/O.
Okay. So yes, so let me explain the MLFQ rule. Okay. MLFQ is just a simple rule. Whenever you schedule a process for execution and give it a time quantum, it says what happened when that process finished its time slice. Did it use its entire time quantum or did it block before its time quantum expired? Okay. If it uses its entire quantum, you are going to reduce the priority of the job. Okay. If it actually is blocked in the middle of its time quantum, you are going to, when it becomes runnable again, you are going to increase the priority of the job by 1. That's the MLFQ rule, okay, which allows you to change the priorities of the job as they execute. Okay. But the question is, why does it do it? Okay. What makes this a good rule? Why could I not have done something else, like not change priorities at all? Yes.
So if you have a lot of I/O going on in your process, it's probably interacting with the user somehow, so it can minimize the response time. Whereas if you have a process that's just using the CPU, it doesn't necessarily matter to the user if it takes a little bit longer.
Okay. So that's a good point. So if you look at what this rule is going to actually do to this processor, remember I said at the beginning there are two types of processes, CPU bound and IO bound. Okay. So you should ask the following question: if I execute a CPU bound, not execute, I actually schedule a CPU bound process on the processor, what's the probability it will use its entire time slice? High. I'm not asking for a number, I'm just saying is it high or low. So it's going to be high because by definition it's CPU bound, it needs a lot of cycles, so it will likely use up its entire time quantum execute. Okay. The opposite is true for IO bound job. Okay. If you schedule an IO bound job, the chances that it gives up its the processor before the time slice expires is going to be high. That's the behavior you expect to see for CPU bound and IO bound job. Okay. Now if you say bump up the priority of any job that does not use its time slice, by definition you are going to start favoring IO bound jobs because those are precisely the jobs that are not going to use their time slice. Okay. So the priority levels of those jobs is all going to rise. Okay. And the opposite is true of CPU bound jobs, because they finish their entire time slice, okay, their priority levels are going to drop. Okay. As a result, if you have, let's say, a 4 level or 4 priority MLFQ scheduler, okay, over time you should expect all the IO bound jobs to be at the top, and all the and the top being high priority in this case, and all the CPU bound jobs to be at the bottom, which means they have the lowest priority. Okay. So we are basically MLFQ is favoring IO bound jobs over CPU bound jobs. Okay, now we should ask, is this a good thing? What does this give us? Yes.
So it makes the experience seem more smooth when like interacting with it. And as someone already said, the IO, like the user will experience, it will seem faster to the user because the processes that they're accessing and that they can see happening
Right.
will be more responsive.
So you will have more responsiveness. To some degree that is true, but all we are saying is the IO bound job is going to go back doing IO. Okay, it's not necessarily saying anything about users interacting with jobs, but yes, what you are saying is also true as an artifact of what actually is happening in terms of favoring IO bound. Okay. Any other thoughts here? Yes.
We're increasing our IO utilization.
You are increasing the IO utilization, true, and you are also increasing CPU utilization to some degree.
Yeah. So just using the CPU. If you're increasing the IO utilization as much as you can, then you'll also decrease your overall what's it called? The
Waiting times, yeah.
turnaround time.
Okay. So that's true. You get that behavior because you are favoring IO bound job. Okay. Now the other thing you should realize is because you are favoring IO bound jobs over CPU bound jobs, MLFQ is approximating shortest job first. Okay. Because our IO bound jobs are actually the shorter jobs in the system. If you go back to that picture I showed you at the very beginning, which is here. So you will see in that picture that because IO bound jobs are short CPU bursts, they look like short jobs because we are only talking about when they execute on the CPU, and CPU bound jobs look like long jobs. Okay. So if you just start favoring IO bound jobs, you are essentially going to start approximating shortest job first without requiring any knowledge of the job length whatsoever. You are not asked what the job length is, you are simply saying I am favoring short jobs, which are in this case IO bound jobs. Okay. And how do you know a job is IO bound? You don't ask for a label, are you CPU bound or IO bound, you simply observe its behavior. Did it finish its quantum or not? If you didn't, you are an IO bound job with high probability. If you did, then you are a CPU bound job with high probability. Okay. So what MLFQ does at essentially as its core is approximating shortest job first without requiring any job length knowledge. Okay. And by just assuming that short jobs are also the same as IO bound jobs and long jobs are essentially similar to CPU bound jobs. Okay. Question.
Would this also decrease the number of context switches?
Will it decrease the number of context switches? In some sense, MLFQ has other properties which also decreases the number of context switches, which I didn't get into yet because the thing that I didn't show you is along with the priority level being different, each queue is also assigned a different time slice length. Okay. The highest priority queue gets the shortest quantum, the lowest priority queue gets the longest quantum. Okay. And this is okay because typically you are running IO bound job in the short quantum. So you don't need to give it a long quantum and block immediately. Short quantum is okay, and CPU bound jobs are sitting at the bottom. Okay. They need to run for long periods of time. It's okay not to context switch frequently in that case because you are maximizing CPU utilization. Okay. So you are actually going to, by having differentiated quantum durations across queues, you are also reducing the number of context switches. Okay. Because if you had the same quantum duration, you would have a lot more context switches for CPU bound jobs in this case. Okay. So lots of properties thrown in. Okay. Approximating shortest job first, shortest jobs are the same as IO bound jobs, change the priorities to actually infer which one is an IO bound, which one is a CPU bound job, use differentiated time slices to reduce context switches. So many things come into play all at once. Okay. And then the thing that was mentioned at the very beginning, which is you also have to throw in something to avoid starvation, because there are lots of IO bound jobs that keep getting activated. Your CPU bound jobs are going to sit at the bottom, get no CPU time whatsoever. Okay. So to do this, if you sit in a queue and do not get scheduled for a certain period of time, you automatically get bumped up. Okay. So, eventually if you have any jobs that are starving, they will rise to the top, they will at least get one shot at the CPU and then fall back, and then that same thing might happen every so often, but you will not be perpetually starved. Okay. Yes.
So at the smallest priority level, the time quantum is larger, right?
At the smallest priority, small meaning high or low? What do you mean by small?
Where the IO jobs
Yes, the high, yes. The IO bound jobs are at the highest priority level. Here the quantum is the smallest.
so at the lowest priority level, time quantum is largest, right?
Yes.
So initially, when a IO job comes, it will go to lowest priority level.
No. So the question, what you do in the system is when a job arrives, you start it at the highest priority level, not at the lowest, just to give it some benefit of the doubt. You don't know what kind of job it is. Yes, if it's CPU bound, it will drop immediately. Okay, so all new jobs, so that's the one thing I didn't mention, all new jobs start at the highest priority level because you don't know anything about that job when it starts. Okay. All right. So that's essentially multi-level feedback queue. Okay, so and then I talked about how you are adjusting priorities. Okay, there's some exercise which I'm going to skip. Okay, and then talk about some other things. Okay, so this also we talked about, which is how do you avoid starvation and so on. Okay, so here's one policy which is a randomized policy. Okay, as the last one we are going to talk about before we switch to what MINIX does, and we'll see MINIX essentially implements MLFQ. Okay, that is why I went through MLFQ in some detail. Okay, but we'll talk about one more before we jump to MINIX, which is called lottery scheduling. Okay, does anyone even remember this? Yes, what is it? No. Okay, so lottery scheduling is a randomized policy where every job is given some number of lottery tickets. Okay, and to decide which process gets to go next, you essentially run a lottery. You take all the lottery tickets from all runnable jobs, and then you pick a winning one, and the job that has the winning ticket gets to run next. Okay, so let's say you give one ticket to each job. Okay, so if there are n runnable jobs, you will get chosen with probability 1 over n. Okay, so over n tries, hopefully you get to run. So it's completely randomized. There's no guarantee that you are actually going to get one time slot every n time slots, but on average or long periods of time that will happen. Okay. Now, what is good about this policy? Why do we want to do things in a randomized fashion? Looks like it's doing what round robin was essentially doing. Any thoughts on why we care about lottery scheduling? Yes.
More like a weighted random choice, right? So
Okay.
based on number of tickets one gets, like the random probability is like weighted.
Okay. Yes, that's right.
Basis on the fact that given enough time, it'll wait out to be fair.
Yes. So over time it is fair, but remember nobody said you have to give only one ticket to each process. I just made that up as an example. You can give as many tickets you want, you meaning the user or the OS, to each process. So what lottery scheduling does is it allows you to control the amount of CPU time each process is going to get over some larger periods of time. So a very simple example, if you have two processes and one process has 2 tickets and the second process has 1 ticket, okay, essentially the first process is going to get 2/3 of the CPU time and the first one is going to get 1/3. If you did round robin, you would have gotten equal. You can't control how many time slices you get. Here you actually control. It's randomized, but you do control by controlling the number of tickets. Okay, so if you want to give a lot of CPU time to a process, you should give it a lot more lottery tickets. It's like increasing the priorities. In some sense, lottery tickets are acting like priorities, but they're not exactly priority. You just increase the chances that that process wins and hence gets to run more often. Okay, so here the interesting thing is by controlling how many tickets each process gets carefully, you can also control what percentage of the CPU time it actually runs on the processor. Is that clear? Okay, and because it is randomized over longer periods of time, it all ends up being fair. And fair here means you should get CPU time in proportion to the number of lottery tickets you have. That's the definition of fairness. Not that every process gets equal time. That's not what is the case. Yes, question.
Don't you, I mean, it approximates SJF, but like, don't you actually have to know which are the short running jobs to give them the most tickets? So it's kind of just as unrealistic as SJF to like,
Right.
if you're going to implement this, then you can like properly implement SJF.
Right. So you are asking a question about the third bullet here, saying I could give more lottery tickets to shorter jobs, and then you would approximate SJF because they would get chosen more frequently or run quickly. That's indeed true. If you to do this, you do need knowledge of whether it's a short job or IO bound job and so on, and without that knowledge you cannot accurately give the number. But sure, if you knew that, you could, right? So that's indeed the case. Based on past history and things of that sort. But that's not the only reason you want SJF. You can just say this, there are two jobs, I just need this job to run more because it has more needs as compared to other, more compute needs, so I just give it more lottery ticket. Independent of whether you are IO bound or not, even across CPU bound jobs you can partition the CPU time across processes. Okay, so 2:1 says 66-33%, right? So that kind of stuff. So here is essentially examples which make it a little more complicated than they have to. Short jobs are being given 10 tickets, but you need to know what short jobs are, as was pointed out. But let's assume you know long jobs get 1 ticket, and so if there are 1 short job, 1 long job, okay, the short job is going to essentially get picked 10 over 11 times, and the long job gets picked 1 over 11 times. Okay, so 91 and 9%. Okay, and then you can work out all those other numbers if you want. You will see that by varying the number of lottery tickets, you can actually vary how much CPU time each job gets. Yes, question.
This is a very similar question to that one, but I guess the question is normally when I run a job, I never specify if it's short or long.
Yes, yes.
So how, how are you going to be able to give 1 ticket to the long job and 10 to the short job?
Right. That's a good question. The question again is, you don't know whether a job is a short job or a long job. Okay, and then how do you decide based on if you didn't know how many tickets to give? So that's a valid criticism of this policy, but that's not how it actually gets used in practice. You are not trying to say long jobs get more tickets and short jobs get fewer tickets, or vice versa. What you are actually doing is you are taking some jobs, they may be all similar jobs, not short or long, and trying to say this job should get this much time and that other job should get this other time.
I guess when like as a user, you run a program, you don't even, at least I can't think of the time that I would say like give this process more priority.
Yes. So as a
system.
Yes. So as a user, you're never asked to assign priorities to jobs. Yes, in Unix there is nice, but nobody uses it clearly, right? But same is true of lottery scheduling. You are not expected as users to say this. And I'll mention where actually things like this get used. Okay. So they are actually used in many other kinds of scenarios, like virtualization is a good example. If you create multiple virtual machines on one physical machine, you can use variants of lottery scheduling to say this virtual machine has more jobs running in it, I want to give it 60% of the total CPU cycles, and this one needs 30%. Okay? So you can essentially partition your CPU. This is not trying to discriminate between IO or CPU bound. It's simply saying I want to give X% of the CPU to this job. How do I do that?
That makes sense.
Right? So that's what it's actually used for. This example is not really the way it gets used at all. Any other questions? So there are deterministic versions of this which allow you to give something called a weight. Weight is equivalent to the number of lottery tickets, and those deterministic versions actually guarantee that every k time slots some fraction actually goes depending on the weight to a certain job. Okay, this is a randomized version. It's very easy to understand. Okay, but there are deterministic versions slightly harder to teach, but they do exactly the same thing. And that's basically what gets used in many virtualization framework. They get used in routers to allocate bandwidth. That's another scenario. So if you have 2 users, one user needs more bandwidth or is paid for more bandwidth, that's how you are actually going to get allocated. Okay, if your cable provider says you can pay for 50 megabits per second or 100 megabits per second, they got to allocate that capacity to you on a larger network. These are the kinds of techniques they are using to do that. Okay? But we will keep that aside for now and come back to scheduling in operating systems. So, with all of what I just said, we can now go and look at what is actually happening in MINIX. Okay? So, MINIX is essentially implemented because it is meant for teaching purposes. It essentially does what you learn in a textbook. It basically implements MLFQ. Everything I said about MLFQ and some other concepts actually what MINIX does. That is not true of more general purpose operating system. Right? Linux does not actually do anything close to what anything we learned here. It has its own thing now, which does order one, constant time scheduling and things of that sort. And when you do multiprocessor scheduling, things get even more complicated. Okay, we did not talk about multiprocessors at all. But MINIX is compact and nice to understand, and what it simply does is MLFQ. So, as I said, when is the scheduler invoked? Okay? All of what I said earlier is still true. When a process exits, you got to invoke scheduler and say what gets to run next. When a process blocks an IO, blocks on a lock semaphore, you got to invoke the scheduler. Okay? And then when a new process gets created, when an interrupt occurs or when a quantum expires, also the scheduler gets to run. Everything I said before still true, okay, in the MINIX case. Okay? This is essentially a picture that shows you the scheduler in MINIX. It is a 16 level MLFQ scheduler. Okay? 16 priority levels. Priority levels go from 0 through 15. Okay? 0 is the highest, 15 is the lowest. So, higher numbers are actually lower priorities. Okay? It is opposite of how we think, but that is how Unix does things. So, they map directly to nice priority levels. In nice, you can say nice and say give it priority 4, it will go to the 4th queue, 5th queue actually, because you start from 0. Okay? So, 16 level scheduler, okay? And some priority levels are used for scheduling OS level tasks, some are used for scheduling user processes. Okay? Kernel tasks run at priority level 0. There are only two things that run there. Okay? That is our system task and the clock task. When we come back to the microkernel, we will see again there are two key components in there. Okay? The system task that essentially implements all system calls. Okay, and there is a clock task that is implementing timing. There is also some IPC that is happening. So, all of that is in the system. So, that is running at the highest priority level. Okay. You will see that device drivers and some of the system processes we talked about, file server, process manager, virtual memory manager, device drivers, that essentially run on priority levels 1 through 4. Okay. Still higher than all user processes. Okay. And then user processes, according to the book, they start at 7. Okay. I believe 5 and 6 are unused. I do not know why, but they are not used. Right. So, they start at 7 and go all the way up to 14. Okay. The idle task runs at 15. Okay. So, idle task is essentially a task as an infinite loop. When there is nothing to schedule, you just run the idle task for a time quantum. Okay. So, it is the lowest, it is always the lowest priority task that gets to run when there is nothing else to do, because you can't really keep the CPU idle. If you keep the CPU idle, the OS will not run. So, you basically run, well, that is not true, but I mean you got to run something. So, you run the idle task. Okay. Now, with that in mind, all of what I said about IO bound job, CPU bound job, that is still true, but only for user level processes. You are checking when you run for a quantum, did it finish that quantum, did it not, you bump its priority level 1 up or 1 down based on that. Okay. The priority of the kernel task is not going to change. Okay, it is always going to be at 0. It does not matter whether it used its quantum or not, it is statically bound to priority 0. Same is true of some system level processes. Okay. As far as what the book says, I haven't verified the code actually, because sometimes there is discrepancy between the book and the code. The book says that system processes are treated no differently from user level processes, which means they can be bumped up or down, but I believe that not all system processes are treated that way. Some are actually pinned to priority levels, but some others might be actually floating up or down like any user process. Okay. So, that is the picture you want to keep in mind. Okay, as far as MINIX is concerned, at some point you will start mucking around with the scheduler. So, you need to know that is how it actually looks pictorially. okay, as a multi-level feedback. Okay. You will see that each queue, each level is implemented essentially as a queue, okay, of tasks linked list with a head and a tail. Okay. So, essentially it is a singly linked list, not a doubly linked list, a singly linked list, and there is always two pointers, one pointing to the head of the queue, one pointing to the tail of the queue. The head of the queue is what is at the beginning, you pick a task there, okay, and then if you want to put it at the end, you have to append it to some tail. Okay. All right. So, I said priorities are assigned with nice. Since this is the first time some of you heard of nice, go to any Linux machine or Mac and type nice or man nice, and you will see what nice can do. Can change the priority of a task, fairly harmless thing to do. Okay, not going to do anything bad for you. Okay. So, idle process runs at 15, system processes kernel tasks, not system processes run at level 0, okay, device drivers 1 through 4. All right. So, users can essentially assign priorities, yes, with nice.
Does nice pin a process to a priority, or does it just put it there? And then
Okay, that's a good question. So, the question is, does nice pin a priority, or does it actually allow it to change? Okay, the answer is actually depends on the OS, okay, because you are doing MLFQ scheduling. If you niced it and stuck it at some level, you cannot do MLFQ on that process. So, what actually happens in most real, shouldn't say real, MINIX is also a real OS, most general purpose operating systems is that there is a concept of a priority and there is a concept of where you are in the MLFQ queue. They are two different things. Okay. So, the priority level kind of allows you to say how you start off, but eventually you are allowed to drift up or down from there. Okay. But yeah, I think the implementation of nice, how it maps to any of this is left to the OS. There is no set requirement. Any other questions? Okay, few more things I want to say. So, the other thing you should know about MINIX is this whole restart task, okay, which is essentially the way you are going to invoke the CPU scheduler. Okay. So, the restart task runs every time few different things happen. Whenever there is an interrupt, when there is a system call, when the quantum expires, you will see that there is a flow chart there which you can ignore for this point in time. But essentially many things essentially invoke saying restart. Restart does not mean you rebooted your OS, it just means that I want to start a new task, okay, execute a new task. So, eventually that task will invoke the CPU scheduler and say a system call has just finished or interrupt handler has just finished, quantum has just expired, what should we do next? Okay, so, that is the entry point to how the CPU scheduler essentially gets invoked. Okay. So, that is an implementation detail, but something you should know because you are going to make some changes to some of these. Now, as far as the scheduler is concerned, okay, the implementation according to me at least is not as clean as one would like. It is spread across multiple files and multiple components. Okay. It is not hard to understand, but they did not have a schedule.c which had everything you needed to know about the scheduler. Okay. It is spread across multiple things. The restart process is actually not process, task is in main.c. Okay, and that main.c also has all of the queues that I was talking about. The heads and tails of all the queues of the MLFU scheduler can be found in that file. Okay. So, the enqueuing and dequeuing of processes is actually done in table.c. I do not exactly know why it is different, but that is where it does it. And then there is a function called sched which essentially decides which queue should a process be added to. That is where the priority levels are getting changed. Okay. And then there is another function called pick process. Okay, that is the one that is actually deciding, okay, this is the process that is going to go next. It is essentially doing a priority scheduling at that point. You take the highest priority non-empty queue, take the head of that queue, schedule that process. Okay. So, it is kind of spread out a little bit, but once you get the hang of it, it is not hard to understand. Yes.
Is this happening in the kernel or is this happening in the process manager?
Okay. Is this happening in the kernel or the process manager? Some of this is actually happening in the process manager, but not everything. Some other things are happening in the kernel as well. A few things are happening in the kernel because some of the data structures have to be changed in the kernel, but you can implement some aspects of it in the process manager. Any other questions here? Okay. So, that is the lay of the land as far as how this implementation goes. We will come back to this when the next lab actually is given out. Okay. This is something just wanted you to understand implementation and how it maps onto the source tree and things of that. Okay. Any questions on this? Any questions on the lab? Okay. Did you see the post I made about the scribe nodes? Okay, we implemented lottery scheduling. Okay, and some of you won the lottery. So keep that in mind. So we'll essentially have you scribe some notes. Okay, so we can then hand that back to the class. Okay, so if that's no more questions, we'll end it here. On Thursday, we'll talk about the process manager. Okay, we'll start getting into how, what processes look like and so on.